Next up, we have Belt, an unobtrusive touch input device for head-worn displays. The paper is from the Institute of Media Informatics at Ulm University in Germany. And the speaker is David Dobbelstein.
Thanks for the introduction and good morning, everybody. I'm presenting a work, Belt, an unobtrusive touch input device for head-worn displays. So there's this nice vision of head-worn displays that allows the user to always quickly access information while being mobile. Nevertheless, there's yet a big problem with social acceptance. Head-worn displays and the interaction with the device are prone to draw attention upon the user. One reason is the look of the device, which nowadays still look like technical gadgets. Even smaller ones, like the Google Glass. Miniaturization might solve this problem in the future. But what about the interaction with the device? For example, voice input is very disruptive and obtrusive to others in many public settings, like in lectures. While media interaction is very spacious and notable to bystanders. Another possibility is to use direct touch input at the device, for example, the touchpad on the Google Glass at the head's temple. However, this is at eye level and therefore also obtrusive, especially in face-to-face conversations. So, how to design interaction that doesn't draw attention upon the user? One way to solve this might be by doing subtle interaction within the hand, on the body, on e-textile interfaces, or with common-looking devices, such as a ring. What we proposed in our work is using a belt as a touch input device. A belt is close to the location of resting hands and way below eye level. It has a firm surface. It can be worn and combined as an addition to a variety of garments. It doesn't have to be washed and doesn't have to survive laundry, such as other e-textile interfaces. And it has a large horizontal surface area that can be used for interaction, such as placing shortcuts to various applications. Next, I want to show you a quick video how the interaction with a belt looks like. Did you see the interaction? Let me rewind the video and carefully watch again on the user's left hand. So actually, while walking, the user is swiping with his hand while having it in the pocket. Our vision of a touch belt is this: a common-looking belt that doesn't expose itself as a technical input device. However, what we built as a prototype is a metal rivet belt that uses rivets for capacitive touch input. A rivet belt obviously has a smaller target audience. However, the prototype allowed us to explore the concept. Here you can see the front and back side of the prototype. Each rivet is a touch pixel and is wired to a touch sensor board on the inner side of the belt. The sensor boards are wired to an Arduino, which is wired to a Bluetooth low energy module. What you see here is just 1 out of 6 touch segments. To cover the whole area of the belt, in total, we had to combine 24 touch sensors, 6 Arduinos, and 6 Bluetooth low energy modules. The modules are covered in a paling woven fabric to protect them. Here you can see the touch sensing with a prototype. The belt has 288 metal rivets, each being 1 touch pixel. We propose to use subtle touch interaction that is well known to users from current technology, which is directional swiping and tapping gestures for selection. This is very similar to the touch interaction on the Google Glass. However, in contrast, the user doesn't have to lift up his arm and can instead rest his hands in the pocket if he or she likes to. In this example, the user is navigating through a reminder application using simple directional swipe gestures and tapping for selection. Further on, the belt can be leveraged for spatial mapping of information. Applications can be opened by tapping assigned locations on the belt. In this example, the user is opening a digital wallet application which is located above his real wallet. When we look at pant pockets in general, people often develop habits as to where to store items, such as keys, a wallet, or a phone. And it's not uncommon to see people tapping their pockets to quickly check whether they carry along their belongings. This metaphor can be used for the belt as well, where users can quickly tap the belt slightly above the pockets to quickly check for notifications or informations. Thanks to kinesthetic memory and proprioception, this can be eyes free. Let me show this in a video where the user opens 3 applications one after another. As you can see, he also has a nice taste in music. Finally, we conducted a qualitative user study with 14 participants that had 2 consecutive settings. The first was with the belt prototype in a lab environment to evaluate whether the spatial mapping and the supple input are comfortable to use. In this talk, though, I only want to focus on the second setting of the study, which was held in public at a heavily frequented university cafeteria. This part in public was conducted by replicating the interaction on a common leather belt instead of the prototype, and also without the Google Glass. This was to only evaluate the social comfort of the interaction, rather than the look of the technical device. We were interested in whether participants are willing to interact on the belt in public and how appropriate the different locations on the belt are for such. We found out that users in general feel comfortable interacting on the belt when the interaction is very short, such as for tapping interaction or very short micro-interactions. For longer interactions, people prefer the areas above the front pockets, which is not surprising given that users often rest their hands in these areas. Interaction at the very front, near the belt buckle, or at the very back was seen as least appropriate, because for social implications, since the interaction can really be misinterpreted. Limitations of the systems are that a belt cannot be worn and combined with all kinds of garments and fashion choices. For example, dresses and skirts do not all match with a belt. Also, depending on weather conditions, pullovers or jackets can cover the belt, making the belt harder to access. For more information on the study results, please see the paper. With that, I want to conclude my talk, and I'm happy to take your questions.